Greetings. We continue our discussion in Chapter 9. I'm going to be skipping a section and coming back to it later. Specifically, I'm skipping section 9.4, which is called the pigeonhole principle. Very simple idea, but I don't think it quite fits in now. This video is going to discuss chapters 9.5 and 9.6. Then we'll come back and we'll do a quick review of the pigeonhole principle. But before we continue, I just want to do a little bit of review. And remember, what we're talking about here are these things called permutations and combinations. So we have permutations and combinations. And let me make my pen just a little bit thinner there. And remember what the difference is between permutations and combinations. In permutations, position matters. And in combinations, positions don't matter. And the other thing I want to remind you of when we spoke about this last time, you could think of this as being like an ordered tuple. Ordered. Let me erase. I made a mistake. Oops. An ordered tuple. Okay, it's my first video of the day. I'm kind of messy. So in other words, over here we might have an ordered tuple like A, B, C. And remember, A, B, C is different than B, A, C. And notice that I'm using these rounded brackets to indicate a tuple. And over here we might think of this as being a set. So that if I come over here and notice I'm using set notation over here. These are the same set because we have the same elements in the set. The order of the elements does not matter. Okay? Over here in an ordered tuple, the order does matter. So we've spent, so far in chapters 9.2 and 9.3, we've been talking about these things. And I want to do just a quick review of that again. So when we were talking about permutations, let's just make up an example. Let's suppose that we have a set with 5 objects in it. So we have some set S, which is equal to S1, S2, S3, S4, S5, something like that. And I want to pick one element. And then pick a second element. So we said that the way we could think about this is that, again, it's like a two-tuple here now. And we said there were actually 2 ways to think about this experiment here. We said we could do it with replacement. And we said we could also consider doing this without replacement. Now, if we do it with replacement, we see that there are 5 elements here. So we see that the way that we can pick the first element, there would be 5 ways to pick the first element. And then if we're going to throw that back in the bag and then pick again, we would still have 5 more elements to pick. So the total number of possibilities here would be 5 squared. On the other hand, if we're going to do it without replacement, we can pick 5 elements for the first position, and then there are only 4 of them left afterwards. And we said we would refer to this as P 5, comma 2. Okay, so these were the two ways of doing of calculating the permutations. And I just want to take a side note here. I hope you've been reading in the book. Notice that P of 5, 2 is equal to 5 times 4. And the point here is that there are two elements I'm multiplying. If I were to talk about P of 5, 3, that would be equal to 5 times 4 times 3. And there are a total of 3 elements here. Okay? Well, one of the things that your book points out is if I have P of n and k, okay, then P of n comma k, whoops, let me get my pen back on. That is equal to n factorial, and watch this closely, n minus k factorial. Okay, watch what happens in the case of P5 comma 3. So that would be equal to 5 factorial over n minus k. Well, 5 minus 3 is 2 factorial. Well, look at what that's equal to. That's 5 times 4 times 3 times 2 times 1. And we're dividing that over 2 times 1. Well, these cancel each other out, and these cancel each other out. And notice I've just got 5 times 4 times 3. So this is a very important result. We'll put it on a big slide right here by itself. So we're talking about permutations. And we want to suppose that we want to select k objects from a set of n objects. And of course the assumption here is that k is less than n. Remember, permutations, that means that order counts, order matters. Okay, so if this is being done with replacement, okay, then the total number of possibilities is n raised to the k. And if it's without replacement, okay, then this is what we're calling permutation of n comma k. And we said that that's equal to n factorial over n minus k factorial. Okay, so that's it for permutations, and now we're ready to actually get to sections 9.5 and 9.6, where we will talk about combinations. Now, here's something I want to point out here. So we're talking about combinations now. So let's consider just the following situation. We've got 5 people here, and we've got Al and Bob and Chuck, and there's Dave, and there's Ed. And I picked these names so it's easy to refer to these people. We can just refer to them as A, B, C, D, and E. These 5 people are going to throw a party, and they need to go to the store, and they need to buy some beer, and they need to buy some food for the bride. And these guys sit around and they say, well, we need two people to go. We need two people to go shopping. Okay, so the question is how many different ways can I pick two people from this group? Well, first of all, let's think about that. I could group Al with Bob. I could group Al with Chuck. I could go Al with Dave. I could go Al with Ed. Okay. I could go Bob with Chuck. I could go Bob with Dave. I could go Bob with Ed. All right. I could go Chuck with Dave, and I could go Chuck with Ed, and then I could do Dave with Ed. Now, here's the thing to think about here. Notice if I have Al with Bob, I don't care about Bob with Al. In other words, notice I don't have BA over here because I don't care. I just need the two guys. I don't care about the order here. So I don't want to count this guy over here. I don't want to, he's not one of the ones I have here. Now, a couple of things to note. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 ways to do this. Okay. Now, if I were to go back and look at my permutation way of doing it, my permutation would say there are 5 individuals here, okay, and I'm doing this without replacement. If I were looking at permutations, it would be 5 times 4, okay? We would be doing it without replacement. That's times 20. But here's the thing that you need to realize here. If I'm picking 2, what's going to happen over here in this count over here, if I have somebody XY, then there's also going to be YX. Okay? And in fact, this is just called a permutation of that. In other words, they're the same elements in here. I've just mixed them up. So the question is if I have a set with 2 elements in it, how many different permutations are there? Well, if I've got 2 elements in it, there are 2 ways that I can put something in the first position, and there's 1 way I can put it in the second position. So the way that I can permute a set with 2 elements in it is just equal to 2 factorial, which is equal to 2. So what that's telling me is that when I look at these 20 over here, what's going on is 10 of them are actually matches of the other 10 in there. In other words, if I were to come in here and look at the 20 that are in here, and I were to come over here and look at these 10 that aren't here, you would say, well, but you haven't counted BA, and you haven't counted CA, and you haven't counted DA. Okay, these are all the ones that are contained in here that aren't contained in here. Okay, so there are exactly this many of them. So notice that in fact, the way to derive this number over here, okay, is we could do the permutations on 5 and 2, but we need to divide it by 2 factorial. Okay? Little complicated. Let's consider another example. Okay, so let's suppose we have the same 3 people again, or the same 5 people, and suppose we need suppose we need 3 people to go to the store. So the question is how many different ways can we do that? Well, we could certainly try and list them. I could have ABC. I could have ABD. I could have ABE. I could have ACD. I could have A, C, E, and I could have A, D, E. Okay, now I could come over here and I could do B, C, D. I could do B, C, E. I could do B, D, E. I think that's all like that. And then I could do C, D, and E. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 possible ways of doing this thing. Okay? Now the thing is I just want you to think about if we were to just do P of 5 comma 3, that's going to equal what? P of 5 comma 3 says, well, they're going to be 5 times 4 times 3, right? I can pick 5 people for the first one, 4 people for the second one, 3 for the third. So that's equal to 60. So if I were to look at the permutations, I would get 60 of them. But let's consider something here now. Let's just pick one of those permutations out. Let's just call it X, Y, and Z. Well, we know that X, Y, and Z is actually equal to X, Z, Y, which is also equal to Y, X, Z, and it's equal to Y, Z, X, and then it's equal to Z, X, Y, and Z, Y, X. So there were 1, 2, 3, 4, 5, 6 of these, okay, that are the same. That have the same elements. Well, again, I want you to think about that. Suppose I have a set of 3. Let's suppose it's S1, S2, and S3. And I want to ask, how many different ways can I arrange these 3 elements in here? Okay, well, I know I can put 3 different values in there, and then I have 2 left over here, and then I have 1 there. That's equal to 3 factorial, which is equal to 6. So that what's going on here, if I want to know how many different ways can I select 3 people from a group of 5, it's going to be P of 5, 3. But then what I'm going to do is I'm going to divide by 3 factorial, because there are 3 factorial different ways to permute all of these. So note that this is equal to 5 factorial over 5 minus 3 factorial times 3 factorial, which is equal to 5 factorial over 2 factorial times 3 factorial. This is a very big result, and this is called the combination. Let me get a new screen here. So note what we're doing here. This is a combination. Okay, and basically what we are doing is we are choosing k elements from a set of size n. Okay, and notice here what we're doing is we're doing it without replacement. Okay, so and there's a notation for this. This is sometimes referred to as, it's written this way. It almost looks like a fraction, but it isn't a fraction. People will say this is n choose k. Sometimes you'll see people refer to it as c of nk. Remember, that's different than p of nk. But in any case, let's just formalize this, that n choose k, which is equal to c of nk, is equal to n factorial over, okay, n minus k factorial times k factorial, right there. And this is very, 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 very important. Right there. Okay, so let's consider a couple of examples here. So this class, this discrete math class, has 7 students. Okay, and let us imagine that Dr. Muffetti contacts all of you and says, look, I need to form a committee from this class. This committee has to go to the dean and report to whether Prof. Bill's videos are any good. And so Dr. Muffetti says, pick me a committee of 3. So the question is, how many ways can you do this? Well, the answer to that is actually pretty simple. It's 7 choose 3. And that's equal to 7 factorial over 3 factorial times 7 minus 3 factorial is 7, 6, 5, 4, 3, 2, 1 over 3, 2, 1 times, now 7 minus 3 is 4, 4, 3, 2, 1. And again, remember, I'm multiplying all of these. But things kind of clean up here. That cancels out, that cancels out, that cancels out, that cancels out. And 3 times 2 times 1 is 6. So this cancels out with that. So we can see there are 35 different ways that you can pick a committee of 3 from 7. Now, if you're looking for a little bit of a homework assignment, you could try and list all 35 of these. Okay? Let's consider something else. I don't know if Namibians play poker. Okay, people in the United States play poker. It's a game that you gamble with, and it's a game in which you are dealt 5 cards from a deck. Cards from a deck of 52. And the question is how many possible cards are there? Or how many possible different hands? And the answer to that is 52 choose 5, which is a rather large number. 52 factorial over 5 factorial. 52 minus 5 is 47 factorial. So that's a pretty big number. Okay, I want to go back to this example right over here. Discrete math has 7 students. Dr. Muffetti says, pick me a committee of 3. How many ways can you do this? Well, we figured out there are 35. Now what I would like to do is I'd like to consider something else here. If I remember correctly, our class is made up of 5 men and 2 women. Okay, so the question I have what is the probability the committee has exactly one woman? Okay, well, let's figure out how we would do that. So what's going on here now is we have to pick 3 people. Okay, and remember we've got 5 men and 2 women. So if I have to have exactly 1 woman, that means I have to have 2 men. So that means that there are 5 choose 2 different ways to pick 2 men, and there are 2 choose 1 ways to pick 1 woman. Okay, and I just multiply these together. This is our old product rule over here. So there are 5 choose 2 ways to pick 2 men. Okay, so that's 5 factorial over 3 factorial times 2 factorial. How many ways is there to pick 1 woman from a group of 2? That's going to be 2 factorial over 1 factorial times 1 factorial. So this is equal to, if I come over here, this is 5 times 4 over 1 times 2. And this is times 1 times 2 over 1 times 1. So that cancels out with that. Okay, and it looks to me that there are 20 different ways to do this. Now recall before we found there are 35 different ways to pick a committee of 3. So that would mean that there are, I'm going to come over here, that there would be 20 over 35. This would be the probability of 1 woman on the committee. Look at how we did that. This is the total number. This is the total number of groups of 3. And this is the total number of ways over here to pick 2 men and 1 woman. So we can see that the probability would be greater than 1/2. Okay? Let's just try one more example like this. Suppose that we have 10 Herrero, and let's suppose that we have 8 Damara, and let's suppose that we have 12 Nama. Okay, and these people are all sitting in a room, and we want to make a committee. 5? Well, the first thing that we note over here is that there are a total of 30 people. So there are going to be 30 choose 5 different committees of 5. Okay? Well, suppose that we want the committee, we would like the committee to have 2 Herrero. We would like the committee to have 1 Damara. And we would like the committee to have 2 Nama. So how many different ways can we do that? Well, if we're going to have 2 Herrero, there are 10 choose 2 different ways to do that. And if it's going to have 1 Damara, there's going to be 8 choose 1 way to do that. And if there's going to be 2 Nama, that's going to be 12 choose 2 ways. That's a 2 to do that. So if I were to ask, what is the probability of 2 Herrero, 1 Damara, and 1 Nama, that in fact would be equal to 10 choose 2 times 8 choose 1 times 12 choose 2, and that would be divided by the total number of committees, and that would be 30 choose 5. Okay? Let's consider one more example of that. These are pretty straightforward. Let's suppose that in a room there are 10 Namibians, and let's suppose that there are 8 people from Botswana, and let's suppose that there are 6 people from Angola. And we want to make a committee of 5. And we want a further restriction on it. We want at most 2 Angolans. On the committee. Okay? Well, the way to do this would be as follows. We can consider how many ways are there 0 Angolans. How many ways are there 1 Angolan? And then how many ways are there 2 Angolans? Okay? And if you want to, we could call this A, and we could call this B, and we could call this C. And the thing to note, these are actually disjoint events. So the answer to our question is, if we want to know how many different ways can I make this committee, it's just going to be A plus B plus C. Everybody follow that? Now, it turns over here to say that there are people from Namibia, there are people from Botswana, and there are people from Angola, when all I am really putting a restriction on is the number of Angolans. This really has very little to do with the people from Botswana or Namibia. So we could actually rewrite this, and we could say that there are 18 people not from Angola And we could say that there are 6 people from Angola. Okay. Now, first of all, if I've got, let's see, there are 24 people here. So the way that I could, how many different ways can I make a committee of 5? And the answer of that, of course, would be 24 choose 5. Okay. But let us open up one more screen here. So we have 18 non-Angolans. And we have 6 Angolans. And we're making a committee of 5. Okay, so the way that we would have no Angolans, well, that would be 18 choose 5, and then for the Angolans, 6 choose 0. Notice that any time you choose something, if I go 6 choose 0, this number over here is just 1. Okay? If I want 1 Angolan, well, that's saying from the non-Angolans, I'm going to pick 4. And from the Angolans, I'm going to pick 1. And if I want to pick 2 Angolans, okay, that would be 18, choose 3, and then over here it would be 6, choose 2. Okay, so the number of ways to make up a committee of 5 that has at most 2 Angolans would just be the sum of these numbers. Okay? Not hard. Okay, so again, combinations. We're almost done. One more thing to talk about. And remember what we've done so far with combinations is it's been without replacement. In other words, think about that. We had 5 people in a room. We had to make a committee of 3. The 3 people were individuals. We didn't have some individual that was repeated a bunch of times. But there are times that you can do it with replacement. Okay? So in other words, your book actually talks about these things called multi-sets. And let's talk about these for a second, and let's contrast them with sets. Now, you know when you have a set, this is equal to this. We know that the order doesn't matter. But we also know that this is the same thing as this. Okay, that if we repeat elements, we just make pretend that they're not repeated. In multi-sets, when they repeat, we do care about them. So when it comes to multi-sets, and I believe that your author is using this notation over here for a multi-set. In other words, we could have a multi-set that looks like this. Now remember, multi-sets are like sets, so that this is equal to this. In other words, we don't care about the order, but there is a match between the elements. And we can see that this set over here has 2 1s in it, and this set over here has 2 1s in it. And this, of course, would not be equal to something that looks like this. Okay? So you can see that what's going on over here is this is a combination because we don't care about the order in which these elements appear, but it's with replacement because the elements can repeat. Now, I'm going to borrow from the web page that I referred you to before I asked you to do the reading, and I think they give a very, very good example there, and we're going to use that one to actually explain the mathematics involved in this. So I want to suppose that we go into an ice cream store. Okay, and we're going to get an ice cream cone. We're going to get a cone with 3 scoops. Okay, we do this a lot in the United States. I didn't see a whole lot of people doing this in Namibia, but I think you all know what an ice cream cone is. It's something that kind of looks like that, and you can eat this. And if we have 3 scoops on it, they're going to be 3 scoops of ice cream on there. And what we're going to assume is that the ice cream store has 5 flavors. And the flavors are vanilla and chocolate and strawberry. And I don't know, pecan, and orange. I hope this works out so we could have V and C and S and P and O. And the idea is that you go into the store, you want to get an ice cream cone, and you tell the person working there that you want an ice cream cone with 2 scoops of vanilla and 1 scoop of chocolate. Okay, so in other words, that might look like this. The multi-set might look like V, V, and C. We don't care. It could be V, C, and V. It could even be C, V, and V. Okay? We don't care what order the person actually scoops the ice cream out, but this is just an indication that we're getting an ice cream cone back with 2 scoops of vanilla and 1 of chocolate. So the question is how many different ways can we do this? Now, it turns out that there's a very clever way to think about this problem. So on the webpage, they say, let's think about the following. Let us suppose that the ice cream is sitting in a freezer, and there are 5 different bins here. 1, 2, 3, 4, 5, and here's vanilla, and here's chocolate, and here's strawberry, and here is, I don't remember the other, pecan, and there's orange over there. And let us imagine that there is a robot right here, and I'll draw a robot that just looks like that. And what we have to do is the robot either has to scoop, I'll put a little O there for scoop, or the robot has to move to the right. I'm going to say move to right. So we talked about before, suppose you go in there and you say, I want to have 2 chocolates and I want to have 1 strawberry. Well, if the robot is standing here just like this, there are 2 chocolates and 1 strawberry. So if he's standing in front of the vanilla, he's got to move to the right. And now he's in front of the chocolate, and we say scoop, and then scoop. And then we say he's got to get 1 strawberry, so we say move to the right. Now he's in front of the strawberry, and we say scoop, and then we say move to the right, move to the right. So this over here would correspond to 2 chocolates and 1 strawberry. Suppose I wanted to do 1 vanilla, one pecan, and I wanted to do one orange. Well, if I'm starting off here in the vanilla position, I'm going to do a scoop, and then I'm going to move to the right. That puts me in front of chocolate. I'm going to move to the right. That puts me in front of strawberry. I'm going to move to the right. That puts me in front of pecan. Now I'm going to scoop. I'm going to move to the right. That puts me in front of orange, and now I'm going to scoop. Everybody get it? So I think you can see that for anything I might order, it can be represented by this. Well, notice a couple of things here. There's 1, 2, 3, 4, 5, 6. There are 7 symbols here. And over here, there's 1, 2, 3, 4, 5, 6, 7 symbols. And inside of these 7 symbols, there are always going to be 4 arrows. And there are always going to be 3 circles. Okay? And I think that you will believe that anything that you can order in this ice cream store can be specified this way. So we can adopt one of 2 things here, and we're going to notice something very interesting. There's something very symmetrical about this. The question is how many ways can I do this? Okay? Well, how many ways can I do this is another way of saying if I have 7 positions, how many different ways can I put down 3 circles? And the answer is 7 choose 3. Okay? This is the number of ways to place 3 circles in one of 7 spots. Okay, well, we can generalize this. Generalization is always where things get scary, right? So let us assume that we have n flavors. Okay, in our case, n was equal to 5. And what we want to do is we want to take k. It helps to know how to spell here, and that we don't have flowers, we have flavors. And we want to take k scoops. In our case, k was equal to 3. We'll notice that there were a total of 7 slots, but 7 is equal to 5 plus 3 minus 1, which is equal to n plus k minus 1, okay? And we are asking, okay, the scoops corresponded to the circles, so we said the total number of ways to do this was going to be 7 choose 3. Well, that's equal to n plus k minus 1 choose k. And that's equal to n plus k minus 1 factorial. Sorry, that's actually one of you calling now. I'll call you back in a minute. So that's n plus k minus 1 factorial over k factorial times n plus k minus 1 minus k factorial. And that's equal to n plus k minus 1 factorial over k factorial. And if I come over here, the k's cancel each other out. That's n minus 1 factorial. Excuse me while I answer the phone from Eliphas. Okay, welcome back. I just spoke with Eliphas Shalango. we're almost done here. Notice that what this is equal to over here is this is just n plus k minus 1. Choose n minus 1. Okay? So the thing to notice is that these are equal. That's pretty amazing if you think about it. Okay? Maybe we should do one more example of this. Let's come over here. File, new. So why don't we assume n equals 6 flavors. Okay, and why don't we let k equal 2 scoops? And the question we're asking here is how many different combinations? And remember, what we're doing here is we're allowing for repeats. This is with replacement. So I don't know. We could say if there's vanilla, and there's chocolate, and there's strawberry, and there's pecan, and there's orange, and let's suppose there's watermelon. Okay. So just remember what's going on here. We could have vanilla and chocolate. We could have vanilla and strawberry. We could have vanilla and pecan. We could have vanilla and orange, vanilla and watermelon. But we could also have vanilla and vanilla. Okay, we're allowing for repeats over here. And remember, in the way that we're counting things here, VP is the same thing as PV. Okay, so what the theory tells us is that this could be either n plus k minus 1, choose k, but it could also be n plus k minus 1, choose n minus 1. So in this case over here, it's going to be 6 plus 2 minus 1, choose k, which is equals 6 plus 2 is 8, minus 1, this is 7, choose 2. And over here, this is going to be n plus k minus 1, that's going to be 6 plus 2 minus 1, and that's n minus 1, choose 5. Well, that's equal to 7, choose 5. Are those really the same numbers? Well, this one over here is 7 factorial over 2 factorial times 7 minus 2 factorial. And this one over here is 7 factorial over 5 factorial times 7 minus 5 factorial. Okay, well, 7 minus 5 factorial is 2. These are, in fact, equal. Okay, and that's the answer. So here is the big theoretical result from these 2 sections here, or actually from these 4 sections. So we can have permutations, we can have combinations, we can have with replacement, we can have without replacement. And remember, there are n items, and we're picking k of them. K is less than n. Okay, so if we're doing permutations with replacement, we know that this is n to the k. And if we're doing it without replacement, this is p of nk. which is equal to n factorial divided by n minus k factorial. Everybody okay with that? If we're doing combinations and we're doing it without replacement, remember this is C of nk, which is equal to n written like that, and that's equal to n factorial divided by k factorial times n minus k factorial. Okay, I managed to squeeze it in there. And if it's with replacements, meaning we are allowing repeats, okay, this is going to be n plus k minus 1, choose k, which is also equal to n plus k minus 1, choose n minus 1. So this is a very important table. That you should all understand. There's a lot going on here. And this table is in the book. Okay? Happy homework.